Hemiacetals and Hemiketals. Before jumping straight into the deep dive of cyclic carbohydrate hemiacetals and hemiketals attack of the hydroxyl group at the electrophilic carbonyl group, given that alcohols are weak nucleophiles, the attack on the carbonyl carbon is usually advanced by the addition of a proton, or as we say, protonation of the carbonyl oxygen. When this reaction happens with an aldehyde, the resulting product is called a hemiacetal. On the other hand, when this takes place with a ketone, the resulting molecule is referred to as a hemiketal. The reaction we see here basically illustrates the formation of an intermolecular hemiacetal. Hemiacetals are intrinsically not stable and tend to favor the parent aldehyde. Thus, to achieve stability, molecules comprised of both an alcohol and a carbonyl group like aldehydes and ketones can instead undergo an intramolecular reaction to form a cyclic hemiacetal or hemiketal respectively. This process will result in forms that are a lot more stable as compared to intermolecular hemiacetals or hemiketals. The size of the ring determines the stability of cyclic hemiacetals and hemiketals. It is established that 5- and 6-membered rings are generally favored stereochemically. Intramolecular hemiacetal and hemiketal formation are frequently come across in sugar chemistry. Just to offer you an example, in solution, around 99% of glucose exists in the cyclic hemiacetal form, and only 1% of glucose exists in the open form. Shown here is a molecule of glucose with its formula C6H12O6. Glucose is represented here in Fischer projection. If you remember, Fischer projection is a convention used to depict a stereo formula in 2 dimensions without destroying the stereochemical information. Here, the horizontal lines represent bonds projecting from the plane of the paper toward the viewer, and vertical lines represent bonds projecting away from the viewer. As we can see here, glucose, as an aldose, has an aldehyde group plus 5 hydroxyl groups. Thus, what we satisfy here is the condition wherein we have a molecule that possesses both carbonyl and alcohol groups. Thus, biochemically, glucose can form an intramolecular cyclic hemiacetal. In the next slide we will see how glucose can be cyclized to a hemiacetal structure as represented here in its Fischer projection. Generally, hemiacetal formation occurs when the nucleophilic hydroxyl group of an alcohol attacks the carbonyl carbon of an aldehyde functional group. In the case of glucose specifically, this reaction occurs intramolecularly between the hydroxyl group of carbon 5 and the aldehyde carbon, resulting in the formation of a more stable 6-membered ring. In the case of glucose, a 6-membered ring is thermodynamically more stable than a 5-membered ring, thus favoring the formation of a 6-membered ring over a 5-membered ring. As a result of the cyclization process, the groups will not anymore located on the left or right side of the backbone. Rather, they will be oriented either upwards or downwards in relation to the ring structure. From the illustration, we can deduce that groups located on the left side of the Fischer projection are now facing upwards. Groups on the right side of the Fischer projection, on the other hand, are facing downwards. And more significantly, in the process, a new chiral center is formed at the former carbonyl carbon in the case of glucose, the aldehyde carbon, which is now called the anomeric carbon. This nucleophilic attack can occur above or below the pi bond, resulting in 2 diastereomer products called anomers. Let's now look more closely at the carbon C1 that was once the carbonyl carbon of the aldehyde. If we will now focus to this carbon in this Haworth projection of glucose, we will now see that this has become the stereogenic or anomeric carbon of the cyclic glucose. We can see here that the OH group attached to the above-mentioned anomeric carbon can either exist in the same or opposite side of the CH2OH group. Glucose can now exist in 2 different anomeric isomer forms or anomers, depending if the OH group is on the same side of the CH2OH group or on the opposite side. These 2 forms are referred to as anomers of glucose and are classified as alpha or beta isomers. Glucose can exist as an alpha or a beta isomer, depending on whether the OH group attached to the anomeric carbon or C1 is on the same side as the CH2OH group or is on the opposite side. If we refer to another conformation of sugars, the chair or boat conformation, or if we move from a Haworth projection to a chair conformation, the groups pointing upwards in the Haworth projection will now become equatorial. Consequently, the groups pointing downwards now become axial or perpendicular to the horizon. Looking at the illustrations here, if the anomeric hydroxyl group is cis or at the same side of the CH2OH group or the carbon 6 group, Then it is considered to be the beta anomer of glucose. Conversely, the alpha anomer contains an anomeric hydroxyl group that is trans or opposite with respect to carbon-6 group or the CH2OH group. In water, the ring-closing hemiacetal reaction of glucose occurs in the forward and reverse directions, resulting in the spontaneous opening and closing of the ring and an equilibrium concentration of the two anomers. Due to steric hindrance, the beta anomer of glucose accounts for approximately 63% of concentration, and the alpha anomer accounts for around 36%. The straight chain form accounts for the remaining 1% of concentration. This is what is being referred to as mutarotation, the change in the optical rotation because of the change in the equilibrium between two anomers when the corresponding stereocenters interconvert. Let us now proceed to discuss Hemiketal formation in sugars. A hemiketal is a compound with this general formula seen here. It is formed by the reaction of acetone with an alcohol. We have just seen the cyclization of aldehyde sugars, the aldoses which possess an aldehyde group and hydroxyl groups. But what happens if the carbonyl group is a ketone rather than an aldehyde? To review, let's look at this structure, which is fructose. Fructose is a ketose because it possesses a ketone group with the carbon 2 for its carbonyl carbon and 5 hydroxyl groups. But instead of cyclizing to a hemiacetal, it behaves differently. It cyclizes to a hemiketal instead. But since the hydroxyl groups at carbons 5 and 6 can attack the carbonyl group at carbon 2, there are in fact two ways in which a molecule of fructose can cyclize. Let's look at the first way. In the first case, looking at the Fischer projection of D-fructose, the hydroxyl attached to C5 attacks the carbonyl group located in carbon 2 and forms a cyclic hemiketal. The product is now a 5-membered ring structure known as furan. Sugars in a furan conformation are known as furanose, and this particular product is called Fructofuranose. However, a second scenario exists wherein the hydroxyl attached to C6 attacks the carbonyl group, resulting in a 6-membered ring or a pyranose form of fructose. The product is called Fructopyanose in analogy with the 6-membered ring of pyran. Thank you for watching this episode in this playlist. Check out the other videos in this playlist, and please do subscribe to our channel and click the bell to be notified of new video episodes that will be regularly uploaded.